there is way more scientific fraud than meets the eye. The magicians that fabricate data and that manipulate data. But what about the ordinary tweaking of model specification and research designs that are going on in order to produce empirical results?
What if the biggest threat to science isn't that it's wrong, but that it looks right? And what if the results we trust most, statistically significant, peer-reviewed, beautifully modeled conclusions, are sometimes the product of something far more subtle than fraud, something harder to detect, easier to justify, and far more common? I'm Autumn Fnaf, and as always, I'm joined by my co-host Noah John Siracusa. We're diving into the credibility crisis in science, where the question isn't just who's lying, it's whether the system itself is quietly bending the truth.
So before we dive in, I just have to ask, I imagine you wrote this book because you really care about science and you really want to help science, so you're calling attention to its flaws so that we can know how to fix them and make the scientific process and profession more robust and stronger and better. But I do wonder, there's so many science denialists and skeptics, especially lately. Are you worried that people will see this and just give more fuel to the flames of science denialism?
I think you could make that argument about almost any rule. So a law against murder, for instance, might be said to put the idea of killing someone into people's heads in the first place. So that's not really a compelling reason to avoid having laws against murder. And likewise, pointing out limitations in the validity of empirical scientific results isn't new. We are definitely not the first ones, and it's extremely unlikely that we will be the last ones to do so. So acknowledging that scientific misconduct exists, that I think is something that everyone knows, or that results are not always fully reliable or, as you have said, robust, is, in my view at least, not conspirational. It is a necessary part of improving the integrity of practice of science. So in a way, everything you say can be misused, misunderstood by someone. And I don't think we have ever experienced that our arguments are being used for or against some arguments of people that have conspiracy theories in their head. And I'm just looking forward for that to happen. I don't think it will happen, but let's see. Let's find out.
Now, out of curiosity, do you think that there's actually more scientific fraud today than previously, especially thinking about AI and YouTube and all of these other channels that are out there that talk about all of the fraud or a conspiracy theory even?
It's a really good question to ask. Unfortunately, one cannot definitely answer it. One cannot decisively answer it. There is no way of knowing. Why do I say this? We only know detected fraud, and that has certainly gone up, and quite significantly so. But that could be for any number of reasons, including that there's much more awareness. There is therefore much more scrutiny. It does not necessarily mean that there is more scientific fraud. All the things that you point towards, they do suggest it's become easier to do fraud. But take AI, it is also true that it is a tool that makes detection of fraud also easier, because all the fraud hunters are now better equipped to go after fraudsters. So it is simply impossible to tell. And I'm sure I would even want to venture a guess.
I may perhaps give you a few answers, not really like a time series type of answer, so we don't really know whether fraud is going up or down. But to put that in perspective, we know from survey results, those that usually use something like Kalichman-style research integrity questions, which are pretty standard for this type of research. We know that roughly 2 to 5% of survey respondents admit to having fabricated or manipulated data, and between 20 and 30% admit to having manipulated empirical results by other means. But these are snapshots over time. We have no such information for the 80s or the 90s, so saying anything, even based on weak indicators such as survey research. We don't know anything about trends, but as times are getting tougher, one might think that fraud is getting more common, but that's completely a hunch, a guess.
Now, I'm curious, is there more fraud today, whether that's an economic one, a technological one? Is this even across fields, or is this more in science in general? I'm curious what your take is on this.
So if you just look at detected fraud, you would think that some disciplines are way overrepresented compared to others. But that is misleading, because it is much easier to detect data fabrication and data manipulation than what we call tweaking in our book, which is, subtle changes to model specification in order to produce certain results. So, for example, psychology is hugely overrepresented, but that's because psychology heavily depends on experimental methods, which is much more prone to, if fraudsters do something, to data fabrication and data manipulation. Whereas, many of the other social sciences will be much more either observational data analysis or causal models, which would much more likely to be resorting to tweaking. So again, there's a big difference between what is detected and what is the actual incidence. It's impossible to say whether some disciplines are actually overrepresented compared to others. We believe it is happening all over the place, and it is happening in very subtle ways, much more commonly than in these outright ways of data fabrication and manipulation.
I mean, it's clear that we focus on these detected fraudsters who then become public figures because their fraud was so outrageous, or there's a story behind it. But I think that's just selection. It's not that these people are more likely to conduct fraud. I'm also not sure it's evenly distributed, but there's very little that we can know about these distributions other than what Eric has already said. Detection is related to the type of research, so it's easier and therefore more likely that experimental research is detected to be fraudulent, but that doesn't mean that experimental research is more fraudulent.
What I find interesting is that in this case, you said more public figures, but with the rise of popularity, with someone becoming a public figure, isn't there also, I'll just put it, a lot more eyes and a lot more potential for someone to become a charlatan in one sense or another, especially when there's money, power, or other incentives to shill a product? They become that snake oil salesman sometimes.
Possible. I mean, let's start with junior scholars. I think junior scholars have more to win or more to lose by not committing fraud. So let's assume we are writing a PhD thesis and we have this wonderful idea, and then it turns out that this idea is not as wonderful as it looked in the first place. What do? So the incentive to manipulate empirical results in this situation is certainly the strongest of an entire academic career. However, if we look at detected fraudsters, they are usually not junior scholars. That they are usually senior scholars. Some of them are really famous researchers that have been detected by whatever. There is more attention devoted to the publications of senior researchers. So the more a paper is cited, the more likely it is that somebody reanalyzes it or checks the robustness of the results, because there is more to win if you point out to a famous figure and say, look, he's wrong or she's wrong on this paper. It's attention, I would say. But the incentives are clearly strongest for junior researchers that have an issue with their research. And it's also true that detective researchers are usually tenured professors.
So building on your comment about citations drawing more attention, we're sort of told this story that science is self-correcting. And I can kind of imagine that a lot of papers that are published, I'll be honest, very few people read. They don't really matter. So in a sense, who cares if those are fraudulent? And if it's a really big, bold claim and an impactful paper, someone else eventually will come along and test it. And should I even worry about this scientific fraud? Won't it sort of just naturally weed itself out over time? Hasn't it always been that way?
Science is self-correcting. The problem is that self-correction takes a lot of time occasionally, or frequently, I would say, and it's very costly. Self-correction takes so long that a lot of people can be seriously disadvantaged by fraudulent researches and fraudulent research.
I'll give you another example. Fraudulent research, even when it is found out to be fraudulent, like Wakefield's finding that autism is caused by vaccine, look what we still have. We have loads of people believing that. Because, even if it's fraudulent, once an idea has been planted in people's heads, it's very difficult to get rid of that again. So the fact that science can self-correct with such delays, and it just does not help. Or it helps, but it is not the solution to the problem.
So is tweaking more common than outright fraud? Because you look at this as that it's not exactly a crisis. It's that just teeny tiny manipulation of data to make a point,
Correct.
but not extreme misconduct.
Correct. And that's the main reason why we think it is indeed more common than outright fraud, if you like, because it is just a tiny little shortcut that one does. Some people may even not fully consciously realize what they're doing, though we think most people do, but it's not regarded as fraud by most scientists, which is one of the main things we would like to achieve with the book, is that the scientific community realizes and accepts that tweaking is as fraudulent as data fabrication and manipulation. And that's why we think, though it's hard to prove, as we pointed out, that it's only a small minority who do outright data fabrication and manipulation. But a lot of people will do tweaking.
Let's get nerdy for a second. So I come from a pure math background where we don't have data for the most part. We don't have p-values and statistical significance. So for someone like me, could you explain what is statistical significance? I've always found that term confusing. What are p-values? And can you try to put tweaking into this framework? Like how does tweaking help with those things, or why is it a problem with those things?
So the origin of significance comes from a very simple experiment. There was this lady in England that pretended that she can taste whether you first poured tea or milk into a cup. And then a statistician conducted an empirical experiment with this. And with the first cup, the probability that she gets it right is 50%. If she cheats and she doesn't know anything and she can't taste it, right? If she just by chance, the probability to be right is 50%. If you do it twice, the probability declines to 25%. If you do it 3 times, to 12.5%. So, and eventually it reaches this level where just by chance you have a probability of getting every answer right, which is below 5%. And that is then the usual level of statistical significance. Of course, in statistical models, the situation is more complicated because it's not right or wrong. We assume that the error is a random draw from a standard normal distribution, and we cannot control that with the data that we have. The data comes from the real life. But so that's perhaps a little bit too complicated, but what it means that in regression analysis, a p-value treats the observed point estimate as true and then asks how frequently random variation in the error process pushes the estimate past zero. Whereas the point estimate depends on whether the assumption that the errors that you have in your data are standard normal. So it's in a way, it's an inconsistent concept. And perhaps more importantly, it's often used to decide whether a true effect exists. And that, of course, is not in line with the stochastic process of that. It doesn't give you an answer to the question whether X has an effect on Y. It just pretends to give you an answer. And the answer might be a probability answer. So it's either more or less probable, but it doesn't give you the truth. And then related to our book and perhaps most importantly, it's really simple to manipulate the p-value. Any different, even slightly different model specifications will give you a different p-value for your variable of interest. So if you want a significant empirical result, you would just have to estimate 3, sometimes 5, sometimes 10, maybe occasionally 25 models, and there will be one that gives you the results that you want to have. So in principle, the combination of statistical quantity of interest, such as the p-value, a hard decision, say, accept or reject a manuscript, and the very nature of the model selection possibilities that you have in your data, they don't fit together. That's usually something you shouldn't rely upon. You should, at the very least, you should add some serious robustness tests to a single point estimate.
So why not just replicate the experiment or the publication? Usually replication fails. I won't say all the time, but you can argue that robustness testing might matter more. Why isn't replication enough, essentially?
So I don't think you could do it before publication. It would halt the scientific process, and it would also be hugely costly, of course. Just look at the sheer number of experiments that are undertaken or of observational data analyses that are published. So I don't think this would be reasonably practicable. It is true that after publication, things have been replicated, and the story has not been very favorable to science very often. Very often, studies fail to replicate, and you could say, well, that's okay, because it's very hard actually to systematically replicate, and it's always questionable whether it's an exact replication. But the interesting bit is that there's structure in the replication results. So if it were just, it's difficult to replicate, then you would expect sometimes the results are better, they are worse. And by better or worse, I mean stronger result, either in terms of statistical significance or in effect size. But what we find is, on average, when we do replication studies, many of the studies have lower sized effects and have higher p-values than the original studies, which would suggest that something like either fabrication manipulation, or we would think much more likely some sort of tweaking is going on.
Which I think is quite natural in that case, because even when you're running an experiment, I've seen it where a lab will move from one research facility to another, and you'll even get slightly tweaked results.
Mm-hmm.
Does it fit the trend? Sure, but that changes a lot.
Mm-hmm.
It's very difficult to keep the environment, the lab environment of an experiment constant. But I would like to define a few terms here that we are clear on what we're talking about. In the book, we define replication and replicability if the model specification is identical and the sample is either identical, which we call narrow replicability, which means we exactly replicate the experiment, if that's an experiment, or we have a different sample, which of course is fairly common if we make an experiment with human beings. It's very difficult, if not impossible, to keep the sample constant. But what the important thing think about replication is that we keep the research design and the model specification constant. With robustness, we change the model specification, and we may also change the sample. We can keep the sample constant, so we can take replication data from other researchers and reanalyze it using different model specifications, or what we are currently doing in this follow project. We just estimate 10,000 different model specifications or all permutations of explanatory variables that the data set allows us to do. But of course, we can also change the sample and change both the model specification and the sample at the same time. That's what we call broad robustness. That should in principle work. So it should be possible to broadly find robust empirical results. But our experience suggests otherwise. So we have reanalyzed and checked the robustness of very many papers over the course of our career. And when we find results that are really robust and replicate well, we tend to be surprised.
It seems to me that one of the issues here is we want the world to have this very simple black and white, that a statement is either true or false. And a p-value is essentially saying that, okay, this thing that you observed didn't happen by random chance. It really was meaningful. So we'll put it in the true bucket. And it's weird to discretize things into a true and a false when a lot of things are in between. So I believe, but I hope you correct me if I'm wrong, that there are some people arguing that we should kind of throw out this frequentist statistical approach of p-values and statistical significance and move to a Bayesian approach, which roughly speaking says, let's just say that everything has some probability of being true. And as we collect evidence, as we publish papers, it maybe increases that probability or decreases it by a certain amount. So why are we pretending everything is black and white when we could just say, yeah, there's a 10% chance that vaccines cause autism. Oh, it turns out they tweaked their data. There's only 1%. Oh, this other study brought it down to a 0.10%. What's wrong with a world like that?
I'm a great fan of Bayesian philosophy of science. I'm not so much a great fan of Bayesian statistics because it doesn't really make such a big difference. Bayesian philosophy of science eliminates this idea of Popper, or so that a theory is either right or wrong. And if you find a single case that doesn't concur with the theory, you throw it away and that's it. Bayesian philosophy of science just suggests exactly what you were saying. So instead of black and white decisions, whether a theory is right or wrong, it gives us a probability distribution about whether it's right or wrong. And different people have different opinions there. But when we conduct a new study, we change this prior distribution of probabilities into a posterior distribution of probabilities. And if the new study confirms your vaccine prediction that it may cause autism, then we should increase our posterior, but not to 1. So we are not fully convinced that this is the case. If the study is very serious and well conducted, then it may have a relatively large effect and changes the prior distribution of probabilities to quite some extent. When it comes to statistics, however, and if you do not insert prior information into your estimator in a Bayesian sense, then the result that it will give you is a distribution of effect sizes, and that is not too dissimilar from a confidence interval of a frequentist analysis. So you can make an analysis slightly more efficient. I say it again because that was also not very good. So using a Bayesian estimator, you usually increase the efficiency of your estimate, which matters if you have few data points. However, beyond that, only large difference Bayesian statistics has on empirical results if you assume that you have prior information. So if you insert your prior information into the estimation. And that's not well accepted, at least not in the social sciences, because that's not too different from manipulating empirical results. So if I insert a very strong prior in my data analysis, then I shouldn't be too surprised if the final results are very close to my very strong prior that I have inserted. So that's very difficult to publish in the social sciences. Maybe there are mathematics journals where these papers can get published, or econometrics journals. But in standard applied social sciences, priors are not really accepted. And then without priors, as I said, you get results which are extremely similar to the confidence intervals of frequentist analysis. You can say the logic of Bayesian is more natural, something awkward with confidence intervals, though I don't think that really is true and that really makes a huge difference. And when it comes to the manipulation of empirical results, it's of course obvious that you can manipulate frequentist statistical regression models as you can manipulate Bayesian statistical regression models. So I think one of the results of our book is, if you want to manipulate empirical results, you will always find a way. Doesn't matter on which method you use, which estimator you use, with model specification you use. Even if you use an experiment, you can manipulate empirical results by tweaking with the sample a little bit here and there.
Thomas is absolutely right. But I would say the very basic idea of Bayesian statistics, that there is no single truth, that is a very good one. And it should inject some humility into empirical scientists. No single paper establishes the effect of X on Y. If anything, it is always only a whole body of empirical research, and we go absolutely astray if we publish a paper and say, we have found that X causes Y. No, you have provided some evidence, perhaps, that X causes Y, but you have never really established, let alone proven. And this humility is what is lacking, I think, in a lot of modern empirical scientific research.
So in reading your book, I love how it wasn't just abstract thought. There was a lot of concrete details. Some of the personalities behind fraud and tweaking were really memorable. So can you tell us one of the stories of these people that really stands out in their book? I'll let you pick who you want to share.
Okay, so the term lying Dutchman was coined by a journalist called Joel Achenbach in an article for the Washington Post, and it was used about a Dutch social psychologist who was actually named Diederik Stapel. He is one of the fraudsters with the largest number of retracted articles. So he has 58 retracted articles. The last time I looked, maybe the number is a bit higher by now, but not much. So he's an interesting character, because after he was detected by two of his research assistants, and he started to talk about the mistakes that he made, and he revealed the incentives and the motivations that he had. And he also coined the term one tiny little shortcut in his autobiography that he wrote about his fraudulent career. And what makes his story a bit sad is that he, at least in his autobiography, he doesn't explain his fraud by the incentive structure. So he doesn't want to make a career. He was pretty famous and well regarded in his research area. But he talks about fraud in terms, or his manipulations of data and later fabrication of data, in terms of being unhappy with the results that he got from his experiments. So he didn't like what he called the dirtiness of the variation of the empirical results that he get. And then he changed a few numbers in his data sheet, and everything was neat and orderly suddenly. And that's what he liked. So he liked easy results, and he manipulated his data to get these easy results. Stronzo Bestiale is a completely different story that is not a real character. The story behind it is that in 1987, if I remember correctly, William Hoover, a physicist, got a paper rejected by a journal, or he got it rejected twice by two journals, and he didn't really like it, so he was upset, and then he added Stronzo Bestiale to the authors and resubmitted it to the Journal of Statistical Physics, and it was accepted. So this was how Stronzo Bestiale got his first publication. And then over time, I think there was a web page, there was an invented university where he worked, and he published a few more papers. So that's, in a way, you would say this is fraud, because manipulating the list of authors is also fraudulent. And there is a little trick by fraudsters, because fraudsters are safest when they work alone. If they don't have co-authors, if they don't have lab assistants. However, almost all papers nowadays have co-authors. So what fraudsters do is they add invented co-authors to a paper to make it look more natural without running the risk of being detected by their co-authors or assistants. So Stronzo Bestiale, in a way, is a funny story, not fraud in my books, but it points into the direction of a real issue with authorship and manipulated empirical results.
I can
So,
assure
go ahead.
our viewers and our listeners that my co-author Thomas Plümper actually exists, and he is on camera here.
I do exist, and so does Eric. I'm sure he exists. I've seen him in reality a few times.
Now, we have voice manipulation software for this, but the distinct difference for anyone who's listening is actually your verbalization patterns.
Okay.
And
There you go.
one thing that's sleeping out when you're describing these characters is half the time you tell these stories, both now and in your book, I feel like you're describing a magician. They have this bag of tricks and they keep it secret. And the first example, you said the line Dutchman, he was like the magician who shared the tricks behind his magic with the audience. The other half the time when you're describing them, I feel like you're talking about a drug dealer, like a kingpin, who has this whole architecture built around, and people have to be vetted. You know, only lab assistants can enter in so far. So it's such this amazing blend of being this kind of criminal enterprise, but also being kind of magical because they're creating truth out of fiction, right? That is magic in a sense.
Big question is, how do we actually fix this concretely? What should scientists, journals, and institutions do differently to come up with a solution to the problem?
Right. So we think that there are two main things that are required. First of all, radical data transparency is required, and also a clear revelation of how transparent the data are. What often invites fraud is when experimental data are privately collected and privately held and are not deposited somewhere under the excuse that it's all confidential and cannot be shared. Well, that is just an open door to fraud. So in the book, we propose a classification system that will allow authors and journals to clearly signal how transparent the data are. The other thing that we suggest is that robust testing would really help, but not robustness testing as it's done currently, which is essentially authors choosing their own robustness test. This is as if cyclists who dope can say, oh, I want this doping test and I want that doping test. It's the same thing. So we suggest that it should instead be reviewers and editors who say, we would like to see these robustness tests. But then, of course, it also requires that they don't make this silly mistake. And we go back to true or false. If something fails a robustness test, it does not mean that it's false. It does not mean it should not be published. It just means if you do this specific model specification, then the result is somewhat different from your baseline model. So those are the two main things we think would really help.
What's one thing that you really want people to take away from this or even change about how science is practiced today? What would that be?
Maybe I start with what we want people to know, and then maybe Thomas can say what should change. The thing we want people to know is that there is way more scientific fraud than meets the eye, because we all focus on those clamorous cases that we talked about, the Lying Dutchman, right? The magicians that fabricate data and that manipulate data. But what about the ordinary tweaking of model specification and research designs that are going on in order to produce empirical results? That is an entirely neglected minefield of scientific fraud, and it is important that readers wake up to this reality.
I mean, when it comes to solving everything and eliminating the problem entirely, there is only one magician's trick that would do it, and that is change human nature, make everyone perfectly honest, and prevent people from lying, cheating, and manipulating. That would be the only trick who does it. Everything else, and of course we agree that this will never happen, unfortunately. Everything else, I would say, are second best solutions. They may make cheating and tweaking and manipulating empirical results less likely, and that would be a great achievement. However, we will never fully eliminate these dirty tricks. What it is, at the end of the day, it's like an arms race. So if those who try to detect manipulation of empirical results improve their techniques, then fraudsters will also step up their tricks. So whether or not one is improving the techniques faster remains to be seen. I mean, the technique that I've talked, the estimation of thousands and thousands of models in the model space, of course, would help fraudsters. They can select models, but it also helps people who try to detect fraud, but because they can see where the reported empirical results sit in the entire distribution of empirical results. So it's a weapon, but the weapon can be used to conduct fraud and to detect fraud, and that's where we are, and that's human nature, right? So I'm reluctant to call it a game, but in a way it is like a contest where we are trying to get better on both dimensions in manipulating empirical results and detecting the manipulation of empirical results. And I will change this, but whether AI favors fraudsters or fraud detectors, we don't know yet.
Science has always asked us to trust the process, but what happens when the process itself becomes optimized? Not for truth, but for publication. And it's also for significance and impact. The credibility crisis in science isn't just about fraud. It's about something much harder to confront. And that line between discovery and distortion might be thinner than what we want to believe. And maybe the future of science doesn't depend on better answers, but on better questions. So, as always, stay curious and stay informed of the world around you. Until next time on Breaking Math.